40 students. Okay, so good afternoon.
Good afternoon, sir.
And we have to work on 2 lab experiments to measure the hydraulic conductivity of soil. One experiment, or the first experiment today, is laboratory method of measuring saturated hydraulic conductivity of soil. And second experiment for the day is in situ or field method of measuring saturated hydraulic conductivity of soil. So in this way, 2 experiments on determination or determining the saturated hydraulic conductivity of soil we need to perform today. So you recall my learning in the class. I told you, let me share the slide. Yeah, here. Can you see the slide? Constant head method of measuring saturated hydraulic conductivity in the lab experiment. Do you recall this learning in the class?
Yes, sir.
Okay. So every time or everywhere we are interested to find out hydraulic conductivity of soil, it's basically the Darcy law, which is applied everywhere in any method, whether it's a laboratory method or it's an in situ field method. It is the same. Q means discharge of water or water that is passing through a layer of soil, that is discharge. In time t, if we have, or per unit time, that is flux, I told you in the class, is the simply relationship between hydraulic conductivity and hydraulic gradient, that is delta H by delta L. So B, that is flow velocity, is simply related by this Darcy law to hydraulic conductivity and hydraulic gradient. If you recall, in this method, I told in the class, if we are maintaining a constant head to a soil sample, that is of L, say height or depth, this is the phase from where water is coming out. It is arranged in such a way that water is coming from down and water is coming out from this phase. So this flow of water that is passing through this soil after saturation, it is basically hydraulic gradient. So hydraulic head exactly at this surface that is applied, hydraulic head is something, and water that is coming out exactly from this phase, it is another head. So this is the head which is maintained on this soil towards the outflow side. If we are taking the difference of applied head because of which water is flowing out from this sample versus water outflow condition in terms of head, we are taking out delta H here. That is head difference because of which flow is taking place through this soil after saturation. And we know the L, length of the sample, soil sample. So we can find out hydraulic gradient, that is delta H by L. And by using the Darcy law, that is discharge for a time t, if we have measured, it is simply K, that is hydraulic conductivity, into hydraulic gradient into area of this soil sample, that is A, and in time t, that is quantity of water, or that is volume of water that is passed through this sample, is Q, is related with hydraulic conductivity, hydraulic gradient area of the soil sample, and the time t for which we have observed this volume of flow. So if we know this relationship of Darcy's law states that flow per unit area of the sample is in proportionality relation to hydraulic head and inversely proportional to the length of flow of the soil. So once we have connected this, we are simply getting this relationship, and we can find out the value of K, that is hydraulic conductivity of soil, is simply discharge of water in volumetric unit, length of the sample L, and it is divided by A, that is the area of this sample, cross-sectional area of this sample, and time T, for which we have observed this flow T, and head difference, that is delta H, and here it is written as, in this particular equation, as H. So this is the simple laboratory arrangement, but we need to take care about this sample collection so that soil is not getting disturbed from its original condition in the field. How we are collecting these samples? By using core samples and Agars, that is arrangement, means one instrument we have core sampler Agar arrangement, so that at desired depth in the soil we are collecting the sample. I will show you in one video how to collect this sample, and after collecting this sample we are taking into water this sample for 24 hours so that it is saturated first. Then we are fitting or putting this sample in a particular arrangement where we have porous plates both sides, which allows water to pass freely to and from this sample out. Why we are putting these two porous plates? So that water pressure is not disturbing the soil sample here in this core. And once it is saturated, simply it is a kind of push flow through this soil, which is basically the property of soil, which allows water to move through this soil. And that is called the hydraulic conductivity under a certain hydraulic head. So this arrangement is made in the laboratory to measure the hydraulic conductivity of a soil sample, which is taken from the field, saturated for 24 hours, put into the system, apply a certain head that is maintained, and measure the discharge that is coming out from this sample in terms of volume Q. So to get an idea how this is measured in the laboratory, I have shared one video in your files section. That is basically files. You can see class material, experiment 2, constant head, measurement of saturated hydraulic conductivity of soil. Can you please watch this video first, and then I will share the observations, experiment observations for experiment 2, constant head method of measuring saturated soil hydraulic conductivity in the laboratory condition. And then we will go to third experiment, that is in situ or field method of measuring saturated hydraulic conductivity of soil. Can you see this experiment 2 file video?
Yes, yes.
Can you please watch this for what time? How much time it will take?
16 plus.
16 minutes. So can you please watch, because it's a little bit overlap. So I will arrange next watch this and then tell me. In the meantime, I'm updating your observations for this experiment here itself. So should we meet at about 3:05 p.m. because it's a 2:45. So 3:05 we will discuss about this experiment, and we will start the next experiment, that is in situ measurement of saturated soil hydraulic conductivity by air entry method. Is it okay?
Yes, sir.
Okay. Please watch this video first. Start. As I told you, hydraulic conductivity is the characteristics of soil which allows water to move inside its layer or through its layers. Now there are two methods as I told. One is laboratory method and another is field method. So in the laboratory analysis, we need to collect the soil samples, prepare the sample to find out the hydraulic conductivity. So suppose we need to take the hydraulic conductivity of soil which is just near the layer. So in that case, we can use the core sampler directly to collect the sample. This is core sampler. We can directly fit into the system here. You can put this, seal this, and up to 15 centimeter soil depth we can take the sample of soil. However, when we are interested to find out the hydraulic conductivity or property of soil beyond 15 centimeter, we need to first clear the topsoil layer up to the desired depth and then use this core sampler to collect the sample. How to clear the soil before the desired depth? We have a wide agar that clears the topsoil first and then core sampler is used to collect the sample. So let us take two samples, one from near the surface and second say after 20 centimeters. So let us take in between 20 to 25 centimeter because this core size is just 5 centimeter. So let us see first from the top surface and then deeper layer soil sample collection. Take the sample. So first we are clearing the soil up to say 5 centimeter. Just clear it, make it a level surface so that your sample is level, right? And then by using this core sampler, that's all. You can take the sample. Just like here, we need to fix this. To there up to full depth so that sample is filled in the core. Since it's take a lot of force to drive directly inside without disturbance, we are taking near surface sample or say up to maximum 15 centimeter by using this press method. However, when we are interested to take sample from the deeper layer, say 20 centimeter or beyond, first we are removing the surface by using the agar. Our topsoil layers are removed by using agar and then we are driving this core inside. So let us take this first sample of near surface, how it is, how it looks like, and then we will see it. Let us keep it outside. Now open this with care, just like here. We are taking this sample out with utmost care, and now this is your sample. Now we need to take this out with care, like this. And now it's most important to remove this extra soil which is over the core. So we need to imported this sample we have collected from surface. So these are sealing so that sample is not getting disturbed. So this is sample, and we need to saturate this sample because we have made this level from the field itself. So we need to saturate this sample for 24 hours. Where? In this water tub. Let us put this sample for 24 hours now. It is filled water in this tub and we are putting so that it is saturated by its own. So these are two samples already we prepared to show you how the hydraulic conductivity is measured. Now these samples we are taking to find out the hydraulic conductivity of topsoil surface. We need to first make this label slowly without disturbing the soil. We have taken as sample both sides, and then it is fitted into the constant head permeameter instrument. Instrument to maintain the constant head in this sample. How to maintain the constant head? This is a simple setting where we put this sample inside a cylinder, means with two sand plates, supplying water or allowing water to go inside this sample, and it is also maintained a constant head from the tap to a what it is called source here, or we can say sump, from where water is going constantly to this sample, and it is maintained in a constant head, and the output of water that is going through this soil is collected at the bottom. So let me show you how it is arranged in overall. So this is a sand filter, we can say. So we are putting first this inside here at the top covering. Then one more sand filter we have at the bottom of this arrangement. Put this straight so that it is balanced. Here, check the space, it's creating problem, right, like this. Then we need to put this sample. Okay, so now we need to put this sample in between two sand filters. However, if we are putting like this, it will not get sealed, so water may get leaked. So what we have here a sealing, that is called washer. We need to seal this arrangement completely by using this washer. Then we need to put an arrangement so that sample is completely sealing. Oh, this is opposite side, this side. Yeah, like this. And the same thing here at the bottom. We need to seal this. And now we are putting our sample in between here without disturbing it. Like this. Yeah. It is now sealed here. Here we have our soil sample in this core that is sealed in both sides. It has sand filter both sides so that soil is not getting disturbed, which is subjected to a constant head which is coming from this water from this tap. It is maintained in this reservoir, and we have an outflow valve here to maintain the head, constant head. If there is excess water, it is drained out from this tube, just like here it is draining out. You can see here it's draining out, and a constant head is maintained. So what is the head on this sample? It is maintained from here till here on the top of this soil surface or center of this pipe, which is subjected to supply the water. And once water is going with this head on this sample, it is passing through this sample and coming out from this tap, which we need to collect the water for a certain period of time, that is basically delta T. So what is the head this sample is subjected? Let us see from the top. From this reservoir, we just see this scale arrangement. It is at 5 centimeters. Just see here. It is at 5 centimeters. So difference from 5 to this down level we have here. Just see here. It is 85 and the center of this tube which is supplying, so we can take 85.5. So 5, difference between 5 and 85.5. So that is near about 80.5 is head which is on this soil sample, and water is coming out from the bottom after passing through this soil. That is basically the hydraulic conductivity. So we need to measure what is the amount of water that is coming out from this sample in a particular time, that is delta T. We can take 2 minutes, 4 minutes, 5 minutes, then increase the time to measure the discharge, that is Q. That is basically, if you have come through earlier, or what I told, Ki or K delta S by L. So, and for a certain amount of time T, and this area of this sample we have taken, that is 5 centimeter in size. So let us measure the water that is coming out from this here. Let us put here, this is graduated measuring cylinder, and water you can see that is coming out drop by drop for certain period of time. Let us measure for 2 minutes. Just wait here. Let me start observation and then we will again test. So for first 2 minutes. So let us take from 4 to 0, or 8 seconds, 9 seconds, 10 seconds. To see water is coming drop by drop from this sample. So we need to measure. Let us take for 2 minutes first. Just 30 seconds, 35 seconds. One more minute. So let us take first sample or first observation for 2 minutes. Just wait. So 1.5 minutes. So now this is coming to 2 minutes. So it's a 2 minute now. Take this. How much amount? This is 6 milliliter. 10, 20, 30, 40, 50 milliliter this cylinder is. So bottom is 5 and now one extra 6 milliliter water in 2 minutes from this. So we need to take samples like this for 2 minutes, then 5 minutes, 10 minutes, 20 minutes, until we are getting a constant rate. Though soil is saturated and for every delta T, it will give you the same amount of water, but we need to observe until we are confident that it is coming a constant rate of flow of water through this sample. And that will be the final rate of or final value of hydraulic conductivity of this soil. So let us observe for at least 10 observations, so that we are confident that what is hydraulic conductivity of this soil. So I will give you the observations, then you need to calculate the hydraulic conductivity of soil. Once again, let me explain you how it is working. So let us show you water is coming from here. It is a reservoir constant head. So from here we are maintaining a constant head on this soil. Soil is here in this core of 5 centimeter length and 5 centimeter diameter. It is subjected to a head of 80.5 centimeter of water, and then water is coming out from here, and we are collecting for a certain time, that is delta T starting to ending, and collecting this observation that water is coming for a design time. And then such observations we are using to calculate the hydraulic conductivity of soil. So I will give you the observations, and you need to calculate the hydraulic conductivity of this soil. Okay.
Yes, sir, we watched the video.
You watched or we watched? What about others? At least 2-3 students should tell me that they have seen this video completely. So everybody?
Yes, sir.
Yes, sir.
Video.
Okay, everybody finish this. So it's important to collect the sample, and there we must take care about the collecting sample so that soil is not compacted in core sampler. We need to cut it to the surface to make the same size of core sample of this sample soil. Saturate this for 24 hours first before putting in this arrangement, means instrument arrangement, and maintain a constant head of water to supply to the sample, and then we need to collect the outflow from the sample. That is the simple observation. Observations I put as experiment 2, live observations for saturated hydraulic conductivity. So you can use, what is the size of core, by the way, here? Is it in video? Core size? Anybody? Length of the sample?
5 centimeters.
5 centimeters.
5 centimeter, and the diameter is as well 5 centimeter of this sample. So you can find out the area, and length is 5 centimeter of this sample. So collected water observations, I have put a word file there, observations for experiment 2. Every 30 seconds at different heads of supply. So you can find out what is the hydraulic conductivity of this soil. Now, if you recall, let me share again the class learning, what it was. This is very much clear. So measuring or estimating the hydraulic conductivity of soil is basically based on the Darcy's law. And if you recall, there are different methods. Here we have laboratory method. First, we have taken into account for our experiment constant head per meter. And second condition, because collecting soil samples is bit difficult, and no matter how much care you are taking, there are possibilities of getting disturbed the soil during the sampling. So what we have another methods which is called in situ or field determination of saturated hydraulic conductivity. And if you recall, I have given you number of methods which can be used to find out hydraulic conductivity in situ or in the field condition. First one is by infiltrometer approximation. You have the first experiment you have already performed, infiltration characteristics of soil. So in this particular approximation, we are assuming that underlying soil where we have fitted this infiltrometer in the soil is homogeneous, means there is no difference in soil particles, but if it is homogeneous kind of soil, there simply we are assuming that whatever it is infiltrating, it is passing through this soil and coming out from the bottom after saturating this soil. So that is infiltrometer approximation, though which is not correct because soil is highly heterogeneous, it is not homogeneous condition. But sometimes in absence of proper measurement of hydraulic conductivity, we can take this information as approximated saturated hydraulic conductivity of soil. Double tube permeameter, there is one another means arrangement where we have double ring condition. In the same way we are measuring the hydraulic conductivity of soil from the inner cylinder measurement of infiltration. Then third one is air entry permeameter, which we have as our experiment for the day today as the third experiment. Then Agar hole method, suppose its water table is very near to the soil surface. What we are doing, we are simply developing a borehole, a small borehole. So water table is very near to the soil surface, so water is here, and we are pumping this water with a constant rate condition so that water table is maintained at a certain depth. So we can simply think about this, that the rate of filling of water to this borehole is equal to the rate of pumping of this water by using a pump. So that could be the hydraulic conductivity of soil, means soil is allowing the rate of flow of water to this borehole at which we are pumping this. Reverse to this, suppose groundwater is far below than soil surface. We are filling this borehole with certain quantity of water per unit time or rate of entry of water or supply of water to this borehole to find out a constant head, and that is approximately hydraulic conductivity of soil in which we have experimented this. So pumping test, reverse pumping test, these are the methods which are performed under presence of groundwater table very near to the soil surface or water table is far below to this ground surface condition. So these are methods. So now the third lab experiment or the second experiment on hydraulic conductivity today, we have taken air entry permeameter. However, in all these methods, one thing is common, that is Darcy's law. Everywhere it is Darcy law which is used to find out hydraulic conductivity characteristics of soil at saturation condition. That is simply discharge, let us take as flux per unit time is simply equal to KIA. From a sample of certain cross section area, discharge per unit time is simply relationship of hydraulic conductivity, hydraulic gradient I, that is delta H by L, and A is the area of sample or the soil we have considered here. Important aspect is only and only to find out delta H. So simply if a sample is subjected to a head, suppose here upside somewhere, we are putting a reservoir of water to supply to this area of soil which is subjected through a certain condition. The water that is coming out at this particular point or particular line in this soil, if it is a ground condition, then it is a big area and we are simply trying to find out what is the discharge condition at the bottom, and this discharge is coming because of what pressure difference. Supply water from here to here and just below to this. So since it is under the soil condition, means it's in field condition, this particular space is not having the atmospheric pressure. Remember, here we have atmospheric pressure above the ground, But below the ground, it is not atmospheric pressure. It is suction pressure that is created because of soil interspace or interspace between soil particles. So it is not atmospheric pressure. So that is creating a kind of suction to drive the water through this sample, which is subjected to a certain head. So what is the head? Just above to this flow face or face of soil, which is passing out through this particular point, and just below to that. If we are able to get these two pressures, we can find out the delta H, because of which this flow is taking place into the soil. And once we know the delta H, that is head difference, because of which this flow is taking place there, we can simply use the Darcy's law to find out the hydraulic conductivity of this soil. And air entry permeameter is one of the method we can use here. So let me show you here. Can you see this slide? New slide. Measurement of the field saturated hydraulic conductivity by using air entry permeameter apparatus. Can you see this slide? New slide?
No, sir.
No. Then I need to reshare it. Okay. Now?
Yes, sir.
Yes, sir.
Okay. Okay. So these are the conditions. Now you have already learned what is hydraulic conductivity, what is Darcy law, factors affecting saturated hydraulic conductivity, type of hydraulic conductivity, lateral and vertical, methods, laboratory method, field method. So it is basically field method of determining saturated hydraulic conductivity by using air entry permeameter. Now these are the experiment number 3. Sorry, here I have not changed. So I have submitted, I have already shared the file and I hope you have gone through it. What it is here, let me try to make a kind of, though it is figure there, but let me try to make it very clear. This is suppose soil surface, right? We have a cylinder, this instrument, what we are using, air entry permeameter. We have a cylinder of size, say 30 centimeter length. It is inserted inside this soil up to say certain 15 to 20 centimeter. This cylinder we have arrangement to seal from the top. And in this sealing, we have arrangement here, 3 openings. One is to supply of water to this cylinder here. We have a reservoir of water that is supplying water here. We have another opening here that is to release the air. Whatever air bubbles are produced because of water movement inside the soil, because soil is initially unsaturated, it has soil moisture as well as air. So which is the moment water is going through this, it is removed. So what air removal valve we have supply valve to this system through this reservoir, and we have one opening here which is connected to a say pressure gauge here. It is called vacuum gauge, vacuum gauge, to measure the vacuum which is generated inside this system at any condition. Let me first tell about the instrument and then I will say when it is generated, this vacuum. Okay, if we are supplying water to this cylinder which is sealed from the top, so these 3 openings has knob to control, means to close or to open. So let us, once inserted this cylinder inside the soil, we are supplying, means it is sealed from the top with 3 openings. So center opening is supply of water into this cylinder. So once we are supplying water to this system inside this cylinder, we need to take care about the soil disturbances. Soil should not be disturbed on the top. So what we are putting some sand layer here and one iron plate here, so that water which is dropping on this surface, it is not disturbing the natural soil surface. And then supply of water is open to fill this space with water by opening this air removal valve, so that any air which is here or the space which is initially filled with air is removed. The moment this space is filled, all air is removed. Supply of water is maintained to a head initially, right? To find out the infiltration or rate of entry of water in this soil sample. So we are first measuring what is the rate of entry of water or infiltration, means DH, what is the rate of head that is decreasing per unit time, ds by dt, that is infiltration rate or entry of water into the soil. We are observing for some time, and when we feel that soil is quite saturated, our front may have reached at the bottom of this cylinder, then we are closing this supply of water from this reservoir. So we need to know what is the reservoir radius, that is called RR, reservoir radius, and this is the cylinder which is performing this experiment. So what is the radius of this cylinder? Moment the front is reaching at the bottom, it will go beyond somewhere here. So suppose this is the, or we can take here, this is the front which is going beyond sometimes, or maybe inside within the cylinder or bottom side. So this is the front. We are simply thinking that what is the rate of flow of water from this waterfront downward, that is the discharge. Basically we are trying to find out a steady state condition of ds by dt from this. The moment steady state condition is reached, we are closing this supply of water. What will happen in this system? Water will try to move further down, no matter whether water is we are further supplying or not, but water will move down. What will happen? From this reservoir, water will go entering into the soil and it will create a space that is free of water. However, the trapped air here inside the soil will feel a pressurized condition, will try to move up because of this air, means water front going down, and air that is trapped inside the pores of the soil will try to move up and will try to fill this space which is getting vacuum here, because creating vacuum here the moment water is entering into the soil. So it is vacuum. And this pressurized air will try to move up, and the moment it is reaching to the bottom of this soil or top of this soil layer, it will expand like a bubble. And if in this process we are measuring the suction head that is created because of movement of water inside the cylinder, creating a suction. So suction we are measuring. So what will happen suction to the suction? Initially there was no suction. When we have closed this tap of supply water, initially it was no suction. After a few seconds or maybe few minutes, there is a suction, means drop in pressure. So suction will increase. Suction will increase, means further suction will increase the moment water is entering into the soil. Trapped air is moving up because of filling, means to fill this created vacuum. And the moment this pressurized air is reaching to the bottom of soil, it will expand in form of the bubble, and this suction will again convert to a pressure condition, means the minimum suction will be created exactly at the moment when this air is reaching to the top of soil surface. So we need to measure this suction pressure. Basically this minimum suction condition is what we are assuming is the pressure or suction pressure or pressure head at the bottom of this front, exactly at the bottom, means this is the water front, exactly below this is the suction pressure condition or pressure condition, that is negative, that is suction, that is not at the atmospheric pressure. However, this air bubble is moving, which is creating the lowest suction to this point at the top of the surface of the soil or at the top of the soil surface. It is not accurate measurement of hydraulic head at the bottom of this front. So what we are taking, we are simply taking 0.5 or half of the air entry pressure at the top of this soil is taken, pressure air entry, that is vacuum here basically, as the actual pressure head at the bottom of this front. And this front is because of pressure that is created due to this water initially. So suppose this is the length which this front has moved. So the length of front plus water at the last when we close this tap, that is HT head over this tank which is supplying water to this front move further. So this is the pressure which is subjected in this soil to create this discharge, and this discharge is happening because of the low pressure at just bottom of this front, that is 0.5 of air entry pressure. Air entry pressure we have measured in this vacuum gauge as PA, and half of that is what we are assuming is the exact pressure in the soil. So PA is air entry pressure is actually the measured pressure in the gauge, pressure measured in the gauge plus height of this gauge from the soil surface, that is suppose G, and plus this L. So this is the simple idea. If we can get the subjected head from the top to this front of water and just front of water head, if we measured by approximation of this air entry pressure into the system, these two conditions are used to find out the delta H. Right? That is simply, what is delta H now? HT plus L minus, because this is the bottom, 0.5 PA, and PA is equal to this. So we can find out delta H, and we know the hydraulic gradient is delta H by L. So we can find out what is the rate of steady state flow condition at the last, that is discharge. Simply we are taking, that is K into I into A. A means area of this cylinder. So in these conditions, we are simply trying to find out what is the pressure condition at the bottom of this front, which is driving this flow towards the downward. And that if we can measure somehow, we can find out the hydraulic conductivity of the soil from which we have made this setup. So this is basically rapid field measurement of air entry value. It is simplest and quickest technique for measuring hydraulic conductivity in the absence of water table. There must not be water table so that it is getting disturbed. So this is the setup. Now you can see the same setup in better picture form. This is the cylinder. We have put some sand here. This is the iron plate, and this cylinder is sealed from the top. It has three openings, one for air escape from this system, one for supply of water from the reservoir, and one to measure the vacuum in the system. So vacuum is measured air is removed when initially we are filling this system, and this supply of water is taken from the reservoir, and the moment we are thinking that water front has reached to the almost bottom of the cylinder, this is just assumption, or simply rate of fall of water per unit time, or ds by dt, is getting constant condition. So in this way, this cylinder for our lab experiment, we have 30 centimeter diameter cylinder, which is near about 30 centimeter, 35 centimeter in height. It is inserted inside the soil 10 to 20 centimeter. Lid assembly is fixed in such a way that there is no entry of air at any moment, otherwise it will be a failed condition. And then we are measuring the ds by dt fall of head in the reservoir until it is getting constant condition. Then theory you have, I hope you have already gone through the file I have supplemented. Methodology you have gone, and I will show you through one video as well. And then we need to make the observations. Observations as well I am supplying, but we need to discuss, we need to find out the reservoir radius, means supply of water. Then reservoir means radius of the cylinder which is inserted inside the soil. G is the height of gauge from the land surface. St is the reservoir water level from the land surface. And L is the length of cylinder inside the soil. But basically L is the water front basically. That is, we have measured cylinder is up to this only, but water front has moved suppose up to this. So this is the length of soil from which we are measuring the hydraulic conductivity. So L is the length of soil or water front up to which water has moved. So we are simply assuming that hydraulic conductivity of this length of soil, what we are calculating. So air entry value for calculation is simply P minimum vacuum gauge reading plus G, that is height of gauge from the soil surface, and L is the simply depth of wet front in centimeter from the ground surface, right? And in this way, let me show you this. This is given though, but let me find out, means try to make this clear to you. If you are measuring ds by dt as constant condition, then rate of fall of water in the reservoir, that is supply reservoir, is simply rate of fall of water means what? ds by dt into area of the reservoir. So area of the reservoir is simply ds by dt into pi r reservoir square. That is simply equal to the discharge, what we are assuming it is going to the bottom of the front, water front. That is K into delta H by L into A, that is the area of the flow. Any question? Somebody want to ask anything? I say no one. Okay. So this is both conditions, means this is the discharge and this is the discharge from supply side, and this is the discharge what we are measuring or what we are assuming at the bottom of this water front it is moving. So these two will be equal. So now this is what is delta H in this case? Delta H is equal to HT, if you recall, supply head plus L, that is the waterfront length, minus that is the exactly at the front bottom, means from where water is coming, what is the head, that is we are measuring here as a vacuum gauge. So that is air entry value of half, because it's going to this pressurized system and reaching here it is the minimum. So half of this we are approximating as exact pressure at the bottom of this water front. and PA is equal to simply pressure gauge minimum value plus what is the height of pressure gauge from the ground G and anything else? L, that is the length of the front. Once you have this, you can find out this is the delta H, and then Q is equal to this. So dH by dt pi RR square is equal to simply K into HT plus L minus 0.5 PA divided by L, length of flow, into area of the system, cylinder which we have inserted into the soil, that is pi RC square. Now you can make this arrangement to find out the value of K, that is dH by dt into L by, and here as well, this side if you are making RR square by RC square in same side divided by HT plus L minus 0.5 PA. That is the same here. However, this is assumed the hydraulic conductivity which is not saturating the soil in this short period of time. So based on the observations, it has been seen that saturated hydraulic conductivity K field saturated condition is 2 times of this K, that is 2 dH by dt into L RR square by RC square divided by simply HT plus L minus 0.5 PA. So in this way we have this equation to find out the saturated hydraulic conductivity of the soil. If we have measured this rate of fall of head in supply reservoir until it is a constant condition, rate of fall, we need to know the minimum pressure head or the minimum vacuum or the maximum vacuum that is created inside the system just before reaching this bubble to the bottom of the soil surface. And if we have these observations, we can find out quickly or in very short period of time saturated hydraulic conductivity of the soil. So now it is observation table that is already given to you, and then finally you need to show your results. First part as the relationship of pressure head and time in the reservoir. What is the pressure head with respect to time, so that we can find out dH by dt. Then air entry value or minimum suction, maximum suction or minimum pressure of soil that we have measured by using the suction gauge, and then we can estimate field saturated hydraulic conductivity of soil, that is K field saturated condition, by using this relationship simply here. So this is your next experiment, and this may be more clear once you are watching the video which I have uploaded to your files, means experiment files. Can you see it here? Sorry. Files in class material, experiment 3, that is KFS air entry. Is it there?
Yes, sir.
Yes, sir, it is there.
Can you please watch this? It is again 15 minutes.
Yes, sir.
Okay. So it is 3:37, 3:40. Let us meet at 3:55. And I will give you observations for this experiment as well. So watch this video for experiment 3, KFS air entry per millimeter, and let me make it clear that you understood the process at least maximum what we can from this video. And if you have any query, you please ask me. It's okay?
Yes, sir.
Just watch this video and let us meet again 3:55 at 3:55. Some portion is repeated, so please ignore that. I will read it this video. And the last part of the video is shooted from the camera because means mobile, because the camera battery was lost. So don't see, means it is like horizontally I am putting the rod to find out the waterfront in the soil, but it is vertical basically. Just watch the video and tell me if you have any query. This is the field method of measuring hydraulic conductivity by using air entry Permeameter apparatus. This is air entry Permeameter apparatus, which has many components, unassembled form. So this is cylinder which is driven up to say 10 to 20 centimeter. Let us see, this is near about 34 centimeter cylinder. So we can insert this up to somewhere 15 to 20 centimeter. So let us have say 15 centimeter. So we will insert this inside 15 centimeter. This is required. We need to find out the radius of the cylinder because RC and RR. So this is cylinder. It is 24 centimeter dia. So it has 24 centimeter dia. You can see here. You can take the 24 centimeter diameter cylinder which is inserted near about 15 centimeter inside the soil. So being it's a quickest method, this is mostly used to find out the hydraulic conductivity of soil in different layers. So if it is deeper layer, we need to first remove the soil of top layer, then insert the cylinder and do the observations. This method is basically supported or supposed to be used when groundwater table is much below than the ground surface. So RC cylinder diameter is 24 centimeter, and let us see what is the diameter of reservoir. Scale, as we can see from here as well, it's not a problem. So diameter of the reservoir is 8 centimeter. So what we are doing, we are inserting this cylinder up to, I have shown you, 15 centimeter inside the soil. Then we are sealing this top surface. It has 3 openings, one for air bubble removal when we are filling this cylinder with water from this reservoir. This reservoir supplies water, it has closing as well. When we want to control the supply of water, we can close it. And this is opening to connect this vacuum gauge to measure the vacuum inside the cylinder, as I told in the class. When soil front is reached to the bottom of the cylinder, we are closing the supply, and once supply is closed, air tries to get up. That creates a vacuum maximum when it is reaching up to the top of this completely sealed condition. So to pouring water, one special care we should take. We should not disturb the topsoil surface. So we are putting this sand, and after putting the sand, we are covering this surface by using this iron plate, so that soil is not getting disturbed and not getting shielded to allow the water infiltrating inside this soil. Now you can see cylinder is inserted inside the soil. Even more than 15 centimeter we put here. We marked 15, but it's near about 17 to 18 centimeter to have more stability. And now we'll need to put the sand here to maintain the soil natural condition without disturbing. So we are putting a sand layer and then putting this plate so that once water is coming from the reservoir on this surface, it is coming on this plate and it is not getting disturbed, the natural condition of this soil. So let us cover this, and to seal this we have a special condition. We have a gasket here we need to put, and before putting gasket we are applying some grease here so that it is in completely sealed condition and air is not entering inside. So once it is arranged, we have nut bolt arrangement here to seal this properly so that air is not entering, and we are supplying water just like from here. Oh, we can put this. Wait. Just like here we apply. Now you can see cylinder is inserted in the inside the soil. Even more than 15 centimeter we put here. We mark 15, but it's near about 17 to 18 centimeter to have more stability. And now we'll need to put the sand here to maintain the soil natural condition without disturbing. So we are putting a sand layer and then putting this plate so that once water is coming from the reservoir on this surface, it is coming on this plate and it is not getting disturbed, the natural condition of this soil. So let us cover this, and to seal this we have a special condition. We have a gasket here we need to put, and before putting gasket we are applying some grease here so that it is in completely sealed condition and air is not entering inside. So once it is arranged, we have nut bolt arrangement here to seal this properly so that air is not entering, and we are supplying water just like from here. Oh, we can put this. Wait. Just like here we apply to close this completely and seal this so that air entry is not permitted. Air entry permeter, you can see, as I told, there are three conditions or three valves. One is air valve. Once water is getting inside, the air inside this cylinder is removed from this. This is supply from reservoir to this cylinder, and this is opening to connect the vacuum gauge. So we have arrangement here to connect the vacuum gauge to measure the minimum hydraulic head at the front of the moisture. So now you can parallelly, once it's parallel it is open and it is closed. So let us close this. Supply valve is open and this is also open. We need to also measure the different heights, or we can say head. So from surface, let us take this height of this cylinder top surface. So how much it is? It is here 18 centimeter, and from 18 we will measure what is the height of this head in the supply when it is reaching to constant condition. So let us fill this cylinder or fill this arrangement with water. So let us fill this arrangement with water. We are filling it. And you will see when it is filled, air is removed. Now you can see the air is removed, air bubbles are removed from here. So let us close this and fill this reservoir. And let us take the observation until it is reaching to steady state condition. So now you can see it starts from 2 and this is for 30 seconds. We are observing for 30 seconds, every 30 seconds starting from 2. So now 7.2 for 30 seconds. Again we are filling this, fill this please, and we will take observation for 30 seconds. So it is starting from 2 for 30 seconds again. Now start. Now let us take the final reading starting from 2 centimeter for 30 seconds. So we have observed many times and it is reaching to quite a statistic. It is reaching steady state flow condition of water inside the cylinder. So finally it is reaching to a quasi-static state, and that is in 30 seconds exactly like this. So it is 3.6. Valve, close the valve and connect this vacuum gauge to this condition. So after some time it will start going to reduce the pressure head. It will start measuring. We need to measure the head from here because it was 18 centimeter to 4.3. This is exactly 96, 96, sorry, 98, 98 centimeter is the C, 98, and 18 we have measured below here. You can see 18 plus 98, 116 centimeter from ground surface to head of water. Now you just see, so vacuum is created inside the cylinder, and the moment the bottom's air is reaching to the top of the soil, it bubbles and it will start decreasing this negative pressure. So pressure will increase. So now it is reducing the pressure inside. It is showing what is the air pressure at the bottom, air entry pressure. The moment air enters into the cylinder after crossing this whole layer of soil, it will start increasing the pressure. So it is decreasing pressure. Every graduated smaller scale unit is 4. So it is, there are total 10 graduated scales. So it is reaching to 40 and middle point is 20. So it is increasing. You can see after reaching the highest point it will start decreasing. So it is near about 10 because every smaller graduated scale is 4 millimeter Hg head. So we need to convert it to water head. So just see, within a few seconds it will reach to a maximum negative pressure, and then will it start decreasing or increase in pressure inside the cylinder. So maximum is near about 13. Just wait. 1.13. It reached to a maximum of 13 and now it is reducing slowly. See, reduced to 12. It has reached to exactly 12 and slowly it will reduce. So this is the right time. We need to remove everything and find out the depth of the front. At the same time we need to measure what is the height of this gauge from the soil surface. So this is exactly 92 centimeter above the soil surface center of this. So 91.5 centimeter. So height of the gauge from the ground surface is 91.5 centimeter, 18 centimeter is the cylinder top height, and from cylinder top height to reservoir is 98 centimeter. And now let us find out what is the waterfront moved inside this cylinder. Now let us close everything here and find out the waterfront moved inside this cylinder to find out the depth of the front. So it is closed. Remove this. Let us remove this assembly quickly as soon as we can. So let us remove this very quickly, very fast. And now this is. Find out what is the front. Here it is about 28, exactly 28 centimeter. Let us take at few places without giving much pressure. It is again here about 28.2. Few more places. Yeah, this is the last. So let us take the front. It is 28.567, 28.7 centimeters. So average we can take 28, 28.5 and 28.7 centimeter. The waterfront has moved inside, so that is basically the front height L finally we are taking, and all the dimensions you have measured. So you can calculate finally the saturated hydraulic conductivity KFS. That's all. Okay.
Excuse me, sir.
Yeah.
Sir, I have one doubt from the class. Like today, we studied about many equipments, right, for measurement of soil moisture.
Yes.
How much does that cost? Like each equipment, maybe tensiometer and all.
Soil moisture measurement instrument.
Yes, sir.
So for instrument, suppose gravimetric method. Jaichand, you are asking question?
Yes, sir. Not
Okay,
about
first.
that.
Okay, first let us finish this lab experiment matter, then I will discuss about that as well. No problem. Okay.
Okay.
Okay. So have you finished watching video for in situ hydraulic conductivity measurement by using air entry permeter?
Yes.
Anybody any question? Any problem in understanding how it is done in the laboratory condition? Means field condition measurement of hydraulic conductivity. Any query? Any problem in understanding, any query related to method, related to instrument, related to observations, anything? So should I assume that you understood it correctly? Should I?
Yes, sir.
Yes, sir.
Okay. So observations are also there in the class materials file, a folder, and file is experiment number 3, lab observations for KFS air entry. Can you see that? I can open to make it clear. Yeah. So it's basically pressure head measured for 30 seconds, 9 times, and it was starting in reservoir head tube, which was graduated or marked to measure the head, or say from beginning to the end point for 30 seconds. It's basically every time we started from 2 in terms of scale from the top, and it was ended at different height from the top. Just like first one was 7.2, then 6.8, and last it was 9th observation 5.6 centimeter from the top, and every measurement was done for 30 seconds. So in that way you can find out what is the DS, rate of fall, means total fall of head. Time it is given 30 seconds, so you can calculate ds by dt in centimeter per second. Diameter of Reservoir, it was 8 centimeter. Diameter of the cylinder which was inserted inside the soil, it was 24 centimeter. Height of above soil surface of water level in reservoir at the time of supply valve is closed, it is given 116 centimeter. Depth of bed front measured by, say, rough method by inserting a iron rod which is going up to certain depth easily, that we are assuming that it is front of water that has moved. So depth of waterfront that has been measured 3 times, and on an average we are taking simply 28.25 centimeter. So height of gauge above the soil surface, it was 91.5 centimeter. And P minimum, the minimum means the scale we have seen pressure head, or we can say maximum vacuum that has been created because of air bubble movement from the bottom, from the front to the cylinder inner space, that was measured 13 millimeter of Hg, mercury. And you have to convert this unit as well in height of water, or head in terms of water height. Then you can use the equation to find out saturated hydraulic conductivity in situ condition by using air entry permeometer method. Observations for second experiment or previous experiment, that is laboratory method, constant head method of hydraulic conductivity measurement, are also given here. So you need to use these 2 observations for 2 different methods of measuring hydraulic conductivity in the lab as well as in the field. You need to finish. If you have any query related to these experiments, you can ask, please. Anybody? Okay, so I assume that there is no query and you have learned. You will finish submitting, means finish writing and submitting these lab experiments by Saturday 5 p.m. So Rajesh and Uday.
Yes, sir.
How many records or how many students have not submitted? Any idea? I will send you today after this class the list of students who are registered.
Total 29 students have, sir.
29. There are total, I think, 62 or 64 students. That comes 31 to each side. And Uday, how many of students have submitted to you?
Around 21, 22. Sir.
So it's a few students have not submitted and you need to mark them late.
Yes,
I will send you the list today, and also you need to please track the presence or absentee records. We can download the attendance from here at the last, and you please mark how many students are absent and how many have submitted. We need to have a kind of summary for evaluation. Okay, I will send you the list of the students who have registered in this lab. Okay, so
excuse me, sir.
yeah.
Sir,
Please.
I had a doubt regarding last lab, sir.
What it was?
So, sir, the values of A and B are coming, I mean, more than 1. So, is that fine, or like the values are wrong?
No. Range must be within 1, from 0 to 1.
Sir, shall I share my screen? Can I show you the solution? I mean, I don't know what mistake we have all done.
What about others? Did you discuss among your friends? Because this is
Yes,
the
sir.
same problem.
Yes, sir. Yes, sir. We discussed this. Yes, sir.
So,
We all think the solution is correct. I think like, and we have done the calculations in Google Sheet, so calculation side also it is fine.
okay, so which method of fitting?
Yeah. So, sir,
Data?
what
Yeah.
I did was that I just took the log of all the values of average infiltration rate and log of cumulative. After that, I plotted the curve of log of that average infiltration rate versus time, and I directly basically draw a trend line of logarithmic scale. So it's completely fitting it, obviously, because the trend line is itself is logarithmic. And then after
1, 1.
that,
It will become 1, 1 line.
exactly,
Yeah.
sir. And
Yeah.
after that, we directly got the equation from the software. And then we take the log of our equation, which is our variables. And by comparing, we got the values. But again, it's not
So
working.
you are fitting by using your learnings. You are not using any software directly to fit this data to a particular form of equation. Is not
Uh,
that?
Actually, we used software, Google Sheet.
Google Sheet is not a software in my way.
I mean, yeah,
Means if
technically
you
it's
technically means semi-technical, we can say. So if
okay.
you are giving the equation that I need to fit this condition, it is Uday.
Yes,
Can,
sir.
can you fit the data by using R or method, any method to these two equations I have given, Costico equation and USDS 64, USSES method
Yes,
64. So can you please check?
yes, sir. I will check, sir.
Okay.
Sir, can I share my screen? I mean, the graphs are already there, so we can directly see that
Yeah,
there's.
you can so. Uday, can you comment on this?
Thank you,
Let
sir.
me see first. Yeah, please share.
Okay, the screen is step also. Uh, Sir, can you see anything?
No, it's a blank black screen. Now it is coming.
All
It
right.
is coming. Yeah, yeah.
Yeah.
It is here. Yeah.
Yes, sir. So here is the graph of normal infiltration rate versus time. So, I
Okay.
mean, there's nothing to discuss here.
Yes.
That,
Yeah,
yeah,
yeah, yeah. Yeah.
that we definitely can't fit any normal curve here.
Okay.
So after that, when we took log, so this blue one is the log of the graph of log of infiltration rate versus time. And this is the equation we are getting using this software. And you can see the value of R square. It's almost perfectly fitting. So definitely it should give correct answer. But anyways, using the calculations, this is the answers we got. A, okay, let me mark this also. Alpha is fine. A and B are like definitely not in the range of 0 to 1.
No,
So
no, no, no. But that is the condition.
exactly, sir. That is the condition, but I
Must
don't know.
be ranging between 0 to 1.
Sir, just to confirm, so in the second
Okay.
case,
Maybe just go back. Go back. Means when you are seeing the infiltration rate, it starts from 0, and that's why it is 1. So that is automatically once taking log of 0 means how much will be there?
I've not taken log because that is
Don't
not.
consider the first
Yes, sir.
observation,
Yes, sir. I've not taken that.
and then we need to fit this.
Yes, sir. So you can see that the graph, yeah. So the graph is like the x-axis is D to 9, the series of J6 to J19. So it is J6 to J19. This one. So yeah. So just to confirm, in the first part definitely would be correct. So in the last lab, you told that in this case specifically in USSCS 1964 equation, we have to
Yeah.
take derivative with respect to time in order to basically remove this constant. So dy by dt we kept as I, and that would become, yeah, here I have written yeah, a alpha t to the power alpha minus 1, and then we took log both sides, and then we basically use the same curve of I here also.
A alpha t to the power alpha minus 1. That is the simple condition. So it
Yes,
will be either if you are fitting to infiltration rate this, or you can even fit to cumulative condition as well. Y
yes, sir.
is equal to A alpha plus B.
Right, we can do that, but that's more complex. So we thought it's easy calculation. So let's go for this only. So basically taking log on both sides here, and we already have the equation of the curve, so we can directly get alpha minus 1 by comparing this. So we can easily get alpha, and using alpha we can easily get A by comparing. So yeah.
So everybody got this relationship.
I mean, we discuss the method, so obviously, like, if everyone agrees with the method, so no doubt everyone will get same
That's
answer.
the problem if one is thinking and rest of the friends are simply taking as granted.
No, sir,
Sir,
actually, there
I
is some other method also. It's not.
Other methods means just fitting by using some software itself without Though it's important to know how to fit this. By least square method, we are fitting usually the graphs.
Right.
So methods, if we know, it is the best way what I prefer. But even if you are taking the observations and giving software simply a way that I need to fit this equation and the value of A alpha and B should be not more than 1 from 0 to 1, it will fit the equation as well. With your, that is another way. Without thinking how to fit this, that is one means new way, or without thinking way, that can also give you the idea that what will be the value of A alpha and B for this soil.
Okay.
But let me talk to means Uday, can you fit this and
Yes, sir. I will try, sir.
take care
Yes, sir, I
about
will.
this, how they are or where they are doing this mistake. Reason being, if they are using logarithmic approach, that should not be means giving the deviation from range of observations means value finally from 0 to 1. So can you please check this and
Yes,
let me
sir. I
know.
will check.
So we will take care about you. Please submit the record and we will share.
Yes, yes, I have already mailed this to Rajesh, sir.
Okay. So Rajesh, you also discuss this with Uday. What
Okay,
is the
sir.
problem? Where it could be the means mistake, and because of that, values are getting more than 1. Any other query?
Sir, about the cost, like.
Okay. So you are asking about the cost of soil moisture measuring instruments, right?
Yes, sir.
Okay. So what we discussed in the morning, these are the methods basically. If you recall, we have 2 methods, direct measurement of soil moisture and indirect measurement of soil moisture, where properties of soil moisture related condition in the soil, just like suction or other things we are measuring, our potential, is not that. So if you are talking about the gravimetric method, it is requiring only a sampling box, a simple weighing machine, and one oven. That certainly you are not interested to use because it's not a quick method. Is not that?
Yes, sir.
Second method is simply what was in the list? That is indirect method, tensiometer. And you recall, because you have already learned in your soil technology classes, second year, tensiometer is so far used up to a certain suction range, that is 0.85 atmospheric pressure. You know why? Because of the porous cup, which is made of particular clay, is allowing air to enter through it. The moment suction is increasing more than 0.85 bar. So it is only working up to 0.85 suction condition. Is not that? You have learned this. You told me, that's why I have not means discussed in detail. But this is the limitation. So porous cups are available, means different quality. If I have one porous cup that costs near about maybe 20,000, but highly precise one. Again, it is difficult to implement in the farmer's field if you are thinking in that way. Third method, neutron probe, which is not allowed and still it is cost near about 5 lakhs, 4 to 5. Yeah. Any question anybody is asking? Will I hear some voice? Any question? Okay. Then electron resistance, pressure plate apparatus, these are all means experimental or field condition for say huge investment is required. Now, if you recall, I have given at the last 2 different methods which are indirect frequency domain reflectrometry, FDR, and TDR, time domain reflectrometry, where characteristics of soil moisture or soil moisture is measured by using the characteristics of resistance, capacitance, and so on. Impedance, we can say anything. So these instruments are available in the market. Capacitance based soil moisture measuring, we can say devices are available, say 200 rupees. But there is our challenge. This is challenge. If we are inserting these measuring devices in the soil, they are surface is disturbed, and after some time they are not getting the right information about the soil moisture. So the challenge is to find out a material which is not getting affected because of maybe abrasion during the fitting or setting inside the soil, or inserting inside the soil because of abrasion. Quality should not be changed, or its characteristics basically should not be changed. And it is measuring for a longer duration of time inside soil when it is, let us keep it there condition, because of salt condition that is available in the soil and water. So accumulation of salt condition. The moment we are trying to improve these two conditions, the cost of the same which is available for rupees 100 or 200 rupees in the market, those are China made. The cost for experiment and precise condition ranges from somewhere 10,000 to 20,000 rupees. So Jaychand, now the question is, for what purpose you are interested to find out this particular device? If it is to set up in the farmer's field, certainly we can use 200 rupees capacitance based soil moisture measuring device, but this will not be working for longer. And it may not be very much accurate as well. So now, which particular instrument we should take?
Sir, no idea. Like, I don't
That's
know
right.
what
We can use TDR, and maybe sometimes if we can improve, there are challenges for us to develop a material which is not getting affected because of abrasion when we are inserting the instrument inside the soil first. Then we can use capacitance based or resistance based condition. Second, if it is a tensiometer kind of arrangement, then we need to improve its working condition. Means rather than 0.85 suction pressure condition of soil, it should work at least 5 bar suction pressure condition. Then we can use properly this device for irrigation purposes or in the field of irrigation management. But these two are not available, and that's why we are trying to find out, or still it is, means everybody is trying to find out how to solve this. Experimental condition is okay, investment is not a question, but we need to measure with precision the soil moisture content of the soil. So this is non-solution kind of answer to you. And if you are a little bit elaborating your query or question, then we can discuss about other things. What could be the possible solution? So any other query if you have?
No,
Jashan?
no.
No. Is it clear now?
Yes.
It's not. But with time you will.
Yes, I got
will.
the answer for the question what I asked, like how much would it cost?
Yes, it's a cost basically. For farmers, we need to reduce the cost, which is reliably. We do not have any particular instrument, reliable and cheaper. Costlier and reliable we have, that is not affordable by the farmer. But for experiment purpose, we can have any of these which are available with a high cost. So we are using it. But the farmer's purpose, we are trying, that is challenge to us to find out the cheaper and having quite long period of applications, means longevity is quite high. Such kind of instrument or devices we are trying to find out. Okay, any other query? Okay, so I hope that you will be submitting these two experiments by Saturday 5 p.m. And that's it. Next week we will have another experiment on soil moisture measurement. Okay. So because you have asked the question on soil moisture measurement, let us have next experiment on soil moisture measurement to learn this.
Okay.
Okay. So no other query. So you are free now.
Thank you, sir.
Thank you, sir.
Welcome. Welcome.
Thank you, sir.
Welcome. Welcome.
Thank you, sir.